Hello, everyone, and welcome. My name is Annelies Termeer. I'm the creative director of the VPRO Media Lab, and I'm moderating the next hour where we'll present the results of the AIxMusic Hackathon, the very first. So welcome to everyone watching, wherever you are around the world. We have 33 participants of the hackathon in the Zoom call right now, and they'll present the results of their work over the past week. So last year, Ars Electronica organized the AIxMusic Festival for the first time. That was in a physical location, a beautiful physical location in the St. Florian Monastery. But since everything is different this year, also the AIxMusic Festival is taking place online. And they were hosting the very first AIxMusic Hackathon to explore the creative potential of using AI in the music arena. And again, this time it was also made possible in a collaboration with the European Commission as part of the STARTS initiative. And in the coming hour, we have the participants presenting the work that they worked on remotely over the past week. So each team will have about 7 to 8 minutes to present the result of or their prototype or their concept and talk about it. If you have any questions to the teams or to me or to whoever is talking, you can share them on Twitter with the hashtag AIxMusic20. So AIxMusic20, and I will check Twitter during the presentations and share the questions with the team members if you have them. And good to know that this stream will also be shared after. It's not only a live stream, but it will be shared on the YouTube channel of Ars Electronica. So if you can always rewatch it, and all the links and references will be there as well. So I think we can start with the first team. The first team is actually Team 2A. And their project is called AIxMusic X Human. And I think we will start first with watching their end result video, just to I'll draw you all in. So I think Mauricio can start the video now.
Life as we know it has been upended by the pandemic. We're forced to separate physically, and our primary means of communication is through technology and screens. We only have this limited range of expression and information when we're behind this frame. You know, we can't experience touch or the experience of being with each other, like their body stature or scent or things like pheromones or intuition, just, you know, that energy you have when you're around someone. But instead of feeling separated by this, our group asked, how can we use this medium, this new way of digitally interacting with each other, not to feel so separated, but to actually understand each other better? We considered what could add more depth to our communication and thought about this idea of sharing emotion and how that's done through music and art, how sometimes you can make music and have this way of sharing an expression or emotion with people that you couldn't do in any other way. In addition to seeing each other's faces on the screen, we wondered how we can express feelings through image or sound over this digital medium and use these technological tools as part of the process. We explored of interactions when humans and machine learning models are together in the musical loop. And we were questioning, when we explore new ways of interacting and using our digital tools, what will we learn about ourselves and each other? This project is the experiment and expression of this inquiry. I'm Amy Carl, and I'm an artist in San Francisco. Pierre will share next with you more about the technical aspect of the project. Pierre, we're not able to hear you.
Hello. So thank you for that. Basically, we thought, okay, what technology are we able to use to basically express our emotion, and how could we get people's emotion? So we decided to go for a emotion analysis, and then this emotion analysis runs on the web browser, and then we decided that instead of doing everything on the browser, we'd send it to two different softwares offline to trigger the visuals and trigger the sounds to create a richer experience for the user. So we have a sentiment analysis, which is, you can see right now, fairly neutral, and then on the right, if I smile, you have basically I'm smiling, and you can see on the right that it's smiling. And if I'm angry, then this is my angry state. So if I show you the stack here, emotion states: angry, happy, and disgust as well, which I won't be able to do, but the emotion state is number 2. That would be this. And so this is the visual part, and then we've made another part which sends OSC signals to MaxMSP, and MaxMSP processes those emotions. And so to go back to this kind of hackathon spirit, we also thought of doing like WebRTC, doing everything on the web, but we decided in the end to go for this solution. And now Ying is gonna present the emotion tracking to you. Ying, we can't hear you. Obviously, in the spirit of the hackathon, what you see here is an evolution of what we've done as we've been working on it this morning, and the video is not as up to date as this content is right now. Ying, we still can't hear you.
Okay, I'm here. So I will introduce this part. It's a web application. It's another part of our project. So we want to set up an application for users to experience, let users to explore the relationship between color, emotion, and music. So it's an interactive website. Let me show you. So now you can see my face on the screen. I just visualize it, and it can recognize my emotion. And I use the emotion data to control the color. So the sound is produced by my musician, our musician. Okay, I think I can pass to.
Yeah, I mean, okay, you can hear me, sorry. The interface was skipping. I'm Sergio. I was the musician of the group. I designed the sound with the feedback of my group mates. I designed all the sound experience of our project. So mainly it was, I mean, as the project evolved and taking in consideration that we were focused on the concept, and that's what we wanted, our message. We ended up with a kind of like automated mixing project that I did in Max for it, which is connected, as Pierre, my colleague, said at the very beginning, with OSC. So it reacts to it's changing the mixing the music. I can change to it so you can hear a bit. It's gonna be fast. Yeah, I'm taking out the video. I'm going back to my mic. So yeah, that was it. It's like it was at the end a mix of the different expressions that of the users that were using were interacting with our project. So yeah, on that I will pass to Suyas, who is the last member to present in our project, and he was in charge of all this connection.
Hi, everyone. My name is Suyash. I want to show a little bit more behind the scene of the web version that we were trying to implement. So as you saw the artistic implementation, this is just bare face tracking. And you can see it's pretty decent. I also wanted to see if, these days we all wear masks, and can we crack emotion behind the mask? Because the algorithm looks at all features of the face. And as you can see, it kind of works just even if I show surprise using my eyes, or if I show happiness. But it's not perfect. It needs more training with the data set with masks. And here below that, you also see the audio visualizer that we wanted to showcase how we're receiving voice input, or I can sing and it will work. So just some more exploration. Thank you very much.
Thanks so much, Team 2A. That looked incredible for a week's work. I think we're already running out of time, but I thought it was interesting. Jing, you shared the link, and did I understand that people can try your part out themselves? Is it online?
Yeah, it's already online.
Perfect. So people can go and try that out. Then we'll move on to Team 2B. And they're called Exploring Memories. And I think Damien will kick off from this team.
Yes, thank you very much. Just wait a second for the slides. Here they are. Yes, so thank you very much. Welcome, everybody. We are Rohit M.A., Eric Thalhammer, and Adrien Piton, and me, Damien T. Jews. And we did the project Exploring Memories for the AIxMusic Hackathon here at Ars Electronica. So let's go to the next slide. Yes, so in the past few days, we were exploring the possibilities of human interaction and machine learning in the context of music, art, and artificial creativity under the topic of designing user interactions when humans and machine learning models are together, of hacking the AI mind, its variation autoencoded in the virtual spatial environment. So, as a proof of concept, on a system which acts like a spatial sequencer, in which the player can move through a 3D space, placing objects in it, which then are sampling MIDI sequences in the latent space of the music VAE model. The resultant sequences are then spatialized as musical audio loops into this environment. So let's talk about the music VAE model.
So for the note sequence generation, we use a pre-trained music VAE model, a variational autoencoder provided by Google Magenta. The model is trained on 2-bar MIDI sequences, so it's trained on symbolic data. To obtain the latent space, we encode a data set of 2-bar loops. The latent space itself is 256 dimensional. And to reduce it down to 3, we use principal component analysis, and we scatter the space in a 3-dimensional space. So let's now look at the overview of the entire system.
So basically for user interaction, we have used a virtual environment where a user can navigate into, it's decorated with a point cloud, and mainly the user navigates and can place objects. And based on the coordinates of the object, we will sample melodies from the music VAE latent space, and in order to give the user a feedback about some style properties of the generated melodies, loops, we will send back a color for example, coloring the object. And as we show on the right side, on the latent space, basically the color gradient has been computed in order to give an idea about the note density of the melodies that are generated when sampling the space. So for example, when the object is placed red, it will correspond to having a melody with a lot of notes. And when it's blue, it will be more quiet melody. And so by moving in the space and placing object, the user gets feedback about what sound, what melodies the model has learned to produce. So that's the first interaction. And then these two modules will interact with MaxMSP patch that is doing the audio rendering based on two things, based on the melodies generated by the music VAE models and based on the current user coordinate, the position, and the relative position of the object it has placed for doing audio rendering and audio spatialization. So now let's talk about the implementation of the virtual reality environment.
Yeah, the explorable 3D space was implemented with Unity, and the setup is actually quite simple. So we have a player camera that can freely fly around in this space that we defined. And with a keystroke, you can spawn so-called sound probe objects, which will then be used as the coordinate points that go to the model. The whole thing is wired with OSC, which actually at the moment is not, because we had a problem there. So this morning we mocked the audio within Unity, so also the specialization, and the audio samples come now from Unity script for the demo you're gonna see in a moment. And as already mentioned, the virtual environment around it consists of a point cloud. And there is one problem here. The latent space we have is roughly cubic, but point cloud scans hardly ever are. So as you see in the right side of the slide, the visuals only cover a certain amount of the space, and it's actually quite unintuitive for the player to also explore samples further up or down. So we're now going to see a short demo video.
So what we have seen in this short video were the basic implementations of the interaction and the modules we were using. There's still some developing missing, so this is still a work in progress. But I guess it gave some kind of clear idea what the system will be capable in the future. But of course, in order to make some kind of meaningful artwork with it, or some kind of installation or performative presentation, one would need to, of course, merge the sounds with the 3D environment, develop an own 3D environment, and training the music VAE model in order to get some kind of connecting system and like linked environment here. So by doing this, this tool would be or like the perspective using this tool is creating, for example, installation soundscapes where the player can, in VR, possibly exploring the space and creates like its own soundscape by doing so. Or it could also be some kind, or in an abstract way, some kind of generative composing tool for virtual reality. So there are quite some possibilities in which direction the system can go. And yeah, to achieve this, there's also improving the interaction.
Yeah, this is basically what we thought of. That it would also be good if you could move or remove those objects that you're placing. So you could move them around and try out different sounds that would be generated and thereby create your own kind of soundscape. And also with scaling and the size of the objects, there could be a lot of optimization being done. And another idea we had in mind that not just the MIDI would be generated, but also how the MIDI is synthesized would come from a GAN synth based on the position within the 3D space. And yeah, that's basically it from our side.
Thank you so much. That looks really awesome. And do you guys have any plans of going on with this project to develop it into an actual physical installation? Have you talked about it yet, or have you just been busy?
Yes, so at least we were planning like continuing the development of it. So yeah, will become a system where we can, yeah, for instance, create a soundscape installation with it. So
awesome.
That's what we planned.
Maybe next year at a physical Ars Electronica. Let's hope for it.
Yeah, sure.
Okay, we need to rush on with the next team because I think we're already behind time. But I think there's a few teams that have a bit shorter presentations. Now we're on to team 1, developing lightweight AI, and Cyrus will kick off.
Hello, we are Group 1. We spent the last few days discussing philosophical and technical issues surrounding the current state of deep lightweight AI, in particular for audio generation. I'll pass over to Stefano.
Thanks, Cyrus. Can you hear me okay?
Yes.
Great. Just to clarify that what I'm presenting now was not implemented during the last 4 days, but is rather my personal approach to using AI for music generation, which I contributed to this group in the context of our theoretical discussions and framework. Okay, so deep learning applications to music generation, it's not a secret, require vast amounts of data. And I argue that this encourages blind and non-critical usage of available data sets, perhaps to the detriment of the musical results, sometimes. Next slide, Cyrus, thank you. So often, regrettably, we just grab data sets without really inquiring about their intrinsic quality. For example, a common strategy to increase the data size is to include MIDI encoded performances, which is proven to be an error-prone method. Here you can see an example showing this issue, and it's taken from a known data set. You get the gist, and it's, the time, the meter is different, the key signature is different, or the inflections are different, and so forth. Okay, Cyrus, next. Despite the need for large amounts of data and the danger of incurring overfitting when not using this, it is possible to work with small, high quality and homogeneous corpora. So we personally edited and curated a bespoke corpus of only 475 multi-track symbolic pieces. Next. And we framed the task accordingly. So we framed the task of modeling this corpus using a neural machine translation approach. So generate a target sentence given a source sentence. Therefore, we prepared a data set of source target musical sentences by making all combinations of pairs of tracks in the corpus. Next. We used the transformer architecture and retuned the parameters. These parameters included the number of attention heads, the epochs, etc. Each model was trained for a set number of epochs, with ranges determined by observing the overfitting behavior of the base model. These formed 180 parameter sets, which we trained simultaneously over 24 hours. We then selected 4 models that were favored by common translation metrics. And as we can see, smaller networks were favored. They're doing pretty well. For the in the interest of time, I include the if you want to listen to some examples, please visit that link on this slide. So smaller networks brings us to the next topic of this presentation. I pass the bat to Cyrus. Thank you.
So one particularly interesting application of lightweight deep neural networks is neural audio generation. So neural synthesis depends on neural networks that analyze audio to produce a representation of it that we can use to have control over the timbre of sound in the process of synthesis. But the current state of AI has largely depended on colossal models with millions, billions of parameters, which require heavy amounts of training, which is significantly detrimental to the environment. And generally, the future of creativity is in the hands of big tech data technology corporations, which are kind of defining how we interact with AI. This isn't being developed from the perspective of musicians who only have bespoke hardware, perhaps embedded hardware, or just their computers. We don't have heavy GPUs on which we can perform inference with neural networks. So we need to develop neural networks that can generate audio in real time and fit the memory constraints of embedded hardware. And it seems like we're still quite far off from seeing neural nets in a Eurorack module. That would be pretty fun. One thing we've seen over this hackathon presented by Professor Islang, which is a pretty interesting development in lightweight AI, is the lottery ticket hypothesis. Now, this depends on finding smaller subnetworks of a very large network and compressing this very large network to achieve a smaller network that provides the same performance as the larger network. So these models can fit on embedded devices such as a Raspberry Pi. But questions that remain open are, how do we select the information to keep, which is aesthetically and perceptually important? And the potential for these models is that we can start using smaller, more bespoke data sets to transfer these models to. But these models still require lots and lots of training, even days perhaps, to find a solution. One application of using lots of networks is perhaps being able to instantiate many at once on your own computer within the memory constraints, and having these networks represent different timbres. We could perhaps scatter an audio sample across these different networks and create clouds of new interesting timbres that we've never heard before. I'm going to pass over to Robert now.
Yeah, thank you, Cyrus. Give me a second. We try to experimentize with some hypotheses. As you mentioned, the problem is with lottery ticket hypothesis is that you finally need to train first this big network. So I asked myself during hackathon what we can really do if you don't have time and if you don't have GPU. So here's one radical idea, not so universal, like lottery ticket, that you are not dealing with any large database, but you are starting with some equations. And then you are proceed this equation by very simple neural network like LSTM or recurrent. And you can make predictions. So you are collecting some parameters you like from your patch in maximum speed pure data or something. And then these meta parameters are computed and processed by a neural network. So here here's example that you can deal with really also in this method with very complex objects defined by differential equations, and it works. So this is very simple but useful method. I'm focused on machine learning, but like meta learning. So I'm not interested if any network is trained in one task. I'm looking for something more general. So here's
Robert,
defined.
Sorry, can I just interrupt? I think we're running out of time. How much time do you need?
Like 2 minutes. I'm just.
Okay, please. Yeah, because otherwise people won't be able to present. Sorry. Go ahead.
Okay. So I developed the concept of meta composer, and actually you are starting deal with smaller networks, which I called modules. And here's like group of rules for composing these small networks. So for example, you have the task, one of this, and a neural network checking you the best or optimal small network which you can combine, and then you will receive like answer to your task. Yeah, so this is my idea. Some results also are from you can check out. I recorded that, put at the night some recording on Git on Bandcamp.
People will be able to listen to it here.
Okay, that's only like small distortion by sound, but anyway, I'm working with like masses of sound events, like millions of sound events, but I don't need to have like GPU for this.
Thanks so much. Sorry to rush you. There's so many interesting things coming out of this hackathon. We'll rush on to Team 3A, Laura and Antonio. Their project is called Soundscape-AI. And please be quick, because we have 2 more teams after you. So
yes,
sorry.
Sure. Hi, we're Group 3A, and our topic was Generate, Interpolate, Orchestrate. We're Laura Ibanez, Antonio Ramirez, Sengun Lee, Satvik Venkatesh, Anja Scheller, Jing Wang, and CJ Carr. Antonio and me will be presenting our project and doing a short live demo.
So there is a new age of music starting, so we can call it the AI aesthetic. So in the 40s, the electric guitar was the technology that allowed rock music to surface. And yeah, with the invention of synthesizers and sampler, EDM, electronic dance music, and most of electronic music came into place. And now we have powerful artificial intelligence models that can help composers and musicians make new pieces of music. But then what is this AI aesthetic? How can we interpret it, and what are like the characteristics of it?
Okay, so our motivation. During Hanoi from Google Magenta's talk, we observed several references to environmental and animal sounds, for instance, bird sounds. Therefore, we concluded that our approach to this AI aesthetic would include turning everyday environmental sounds into before unheard soundscapes. This intends to make us change the perception of our environment by breaking its patterns and transforming them into a new hearing experience with the means of AI technology. It will also mean finding a new way to capture the unique atmosphere of a place by turning noises into instrumental sounds, and by that creating an additional level of sensual experience.
Yeah, so the key concepts in our work can be reduced to environmental sounds. So I guess these are soundscapes and field recordings of ambiental sounds. So let's say you go to a park and you record the sound you hear. And we want to convert these to existing musical instruments. In this case, we are using 4 different string instruments that we will show later. And yeah, for these, we use 2 techniques based on deep neural networks. The first one is source separation, which is basically taking sounds from sounds mixed that have multiple sources and try to separate these sources. And I'll also go into detail a bit more on what we used. And neural style transfer, so using the AI to go from one sound to another. So in this case, from environmental sounds to musical instrument sounds.
Okay, so our project steps. The first thing was to find the right sources, which in this case was the field recordings from different environments. We've chosen 3 environments. The first was a beach scene. It had seagull sounds and sea sounds. The second was a park scene with sounds from children and birds. And the third was a construction site scene.
Yeah, so from these sounds, we then used open and mix, which is a source separation algorithm. This algorithm was trained to split sound into vocals, drums, bass, and other sounds. And basically the way this was trained was using multi-track recordings and use them as the loss for a mixed track piece. And then the model is able to learn on how to convert a mixed track into normally a mixed track which has all these elements, right? And it can learn how to convert them to 4 stems, to the isolated segments. And basically, I mean, this is completely oriented towards, let's say, more popular music with all these 4 stems. But in our case, we are feeding it the environmental sounds as an input, and we are trying to obtain the 4 outputs of this. So I guess it also creates some kind of artifacts in here on the separation, because for example, the vocals, normally it goes for the bird sounds or the children sounds in the park. And then the drums go for more percussive elements of these soundscapes.
Okay, so next we've used DDSP library, which is from Google Magenta, to perform timbre transfer on these obtained stems. And so we've used both pre-trained models, in this case a violin, and also our own trained models, which are a double bass, a cello, and a viola, which we've trained during these days. So we've associated each of the stems to one of these instruments, the vocals to a violin, the drums to a double bass, and the bass to a cello, and the other elements to viola. Obviously, the vocals, drums, bass, and other will be other things than this. So the findings when training these models were that quality and homogeneity are better than quantity in DDSP, which means that less data, but with similar recordings and similar performers, are better than more data from separate sources. Okay, so to show our project, we've created a web interface which recreates each of these environments by using mixers and crossfaders. And I'm going to show it briefly. Okay, for each scene, I will first play the original recording, which here is separated into the 4 stems, but I will play it together. And then I will slowly convert it to the transferred version. This is the construction site scene. So this is the park scene. this would be the beach scene. Okay, so
as a bonus material, just a quick thing, you can experiment with the website. It's open to everyone. So as a final thing, we started with a different idea a bit, which was taking existing music and render it with bird sounds. And basically we have an example here. So that didn't work very well. So that's why we changed. But we have Satvik singing Over the Rainbow first.
Somewhere over the rainbow.
Yeah, and then we tried to use the timbre transfer from DDSP with two models we trained, so the red cardinal and the seagull. So let's listen to the red cardinal. And I guess the seagull example is more clear.
Wow.
So that's how a seagull would sing.
So like I can totally imagine the whole seagull orchestra.
Thank you. That's it.
Thanks a lot.
Thank you for watching.
I'm gonna, thanks, Laura. Let's quickly go to Team 3B. With I think Max will take over, and then Zheng, I'm just gonna check with you because you guys have the video. You're up after them. That's a shorter one, right? I think that's only a few. Yeah. Okay. So we should have enough time because they've given us until 3:30. So take it away. Max.
All right. First of all, thank you to the festival. I want to thank my wonderful teammates, Berker, Marco, Anna, myself. Well, I don't need to thank myself. Thanks to Denis and thanks to Joseph. Our experiment is called Breaking Models to Learn About Models. So we used DDSP, which was just used to beautiful effect in the previous presentation. One of the things that we really liked about this was the idea of timbre transfer, which is basically you take a recording with one instrument, like a violin, you remove its melody and loudness, and you get this essence of timbre, and you can move it onto some other instrument. There's a schematic. Now, this is an interesting research question, especially from the perceptual side of things, which is, what is timbre in general? This model gives us kind of an interesting insight into that. You have this sort of maybe problematic definition from the Acoustical Society of America that it's, and I'm paraphrasing here, it's that thing that lets you tell the difference between two sounds that have the same loudness and pitch. So if I play a violin that's medium loud at a C and I play a trumpet that's medium loud at a C, the difference between those two things is the timbre. Is that really the case? Well, maybe DDSP will help us find out. So here's an interesting timbre that we found online. So marxophone. Cut that short in the interest of time. So this on the right is basically what the model sees, at least in this iteration. There's the loudness, it's just how loud it is over time, and you can see that it's kind of bouncy, and that's because these hammers are bouncing on the string. It's very much a character of the instrument. And there's the pitch contour, which is the melody. And according to this ASA definition, everything else should be the timbre, the timbral essence of the instrument. I want to mention that one of the things we really appreciated about working with DSP is that it's so fast. And This is just maybe a lesson for AI in general. It's nice, but it also really changes the way that you interact with the technology. We could train it within a couple of hours instead of some of these things are months, and of course there's environmental concerns for that too. But because we could train it so quickly, that allowed us to develop this exploratory approach where we're like, okay, well, let's just see what makes this thing tick. Let's map as many possible melodies as we can to as many possible instruments. And we had some interesting discoveries along the way. This technique, also known as pair everything with everything. So we developed 18 instruments in a short period of time and cross-pollinated those with 18 melodies. That's 324 sounds. And I say plus because it's a script that's running. This repository is growing. Many of these sounds are a minute plus long and make for very interesting listening. We got everything that you'd hope to get out of a situation like this: a subtractive synth playing Mariah Carey. And why stop there? A subtractive synth making dog barking sounds. Naturally, with great power comes great responsibility, so we had to make the Jimi Hendrix electric guitar singing Heard It Through the Grapevine as performed by Marvin Gaye. This is all just a bit of fun, of course. One of the things, we were very lucky in the group to have a talented electroacoustic composer, Anna, and we took one of her pieces called Phonation, and we used that to train a timbre and wanted to test how much that would transfer. In this case, we used Oh Superman by Laurie Anderson, just cool enough on its own, but even cooler now, arguably. Move forward in the interest of time. But I do want to say that we're going to put this up on a Dropbox. There's lots of sounds, and I think it could be very educational if you want to check it out and see what cross-pollinates well with what. Again, because we could iterate so quickly, we could do these cool experiments. Denis in the group had this really interesting idea of taking the sounds from an 808 drum machine, putting them individually one after another, the kick drum, snare drum, hi-hat, into one long file and trying to train a timbre of that. Now, this is interesting because really each one of these sounds is its own timbre. So there's a multitude of timbres in this file, but we got it to train one thing. And then we wanted to probe what it could do. So we built a very clinical pitch that just sort of steps up all of the chromatic MIDI pitches and just spiked it with a loudness amplitude envelope that you can see here, just like a decaying, exponential, kind of generic percussive envelope. I'm going to play the sound, but it's not super easy to hear. What you'll hear is that in the low tones, it's a kick drum. And then as it goes up, it starts to get a little bit sharper, a little more noise. It becomes a snare drum, and then it becomes a clap, and then it becomes a hi-hat. Let's see if I can scan through that. Wrong song. It's a really interesting finding there. Now, what about this question of timbre as being the thing that isn't loudness and pitch? Well, going back to that marxophone idea, here's the marxophone, and here's something that we built from the marxophone timbre that we extracted, and we gave it to a melody line that was from a synthesizer. And the results, I think, speak for themselves. Now, you can hear that's nothing at all like the timbre that we were expecting. And the lesson is that in the marxophone, all of the bounciness that is so integral to the sound is carried in the loudness, it's carried in the amplitude envelope. And what's more, this synth melody that we trained it on had this vibrato in it. And that vibrato is very much part of the synth sound. It's part of the synth timbre. So really, this is just kind of a neat toy example of how pitch and loudness are a part of timbre too. So that was kind of a fun discovery. Now, as we were doing this, we were dumping all the sounds into a Discord where we were chatting with each other. Anna was listening. She was also asking for speech samples. I have a bit of a cameo in this sample coming up. So Anna, we're very lucky to have a talented composer who created this piece of music based on these samples that we were generating. And Marco in the group created some visuals, and I'll just jump over to that right now. But first, let me say thank you again to the organizers. Thank you to the festival. Thanks, Maurizio. Thank you to my wonderful teammates. And I'll play this, and that should send us out. Alchemy that's universal. And that's pretty cool. Not that long ago.
Thanks so much, Max and Team 3B. Great work. And have a look at that Dropbox if you're interested in watching. I think we'll put up all the links together with the stream. Okay, I think we're doing okay for time, and we're up. We came onto the last team, which is Team 6, and they're called Dialogue. And I'll hand the mic over to Zeng.
Hi, everyone. We're a group of composers and programmers, computer scientists and music lovers. We want to create a music piece that embodies the dialogue between human and a machine in the musical creation process. Our project is a musical piece composed collaboratively with our human composers and the music transformer model from Google. Our composer, Marcin from Poland, first played a melody on his flute. As a response, we left the transformer model harmonized it. And based on the AI's and Marcin's melody, I carried on the music with another melody and then let the AI harmonize that one. As the piece progresses, I further developed the piece by starting an 8-bar harmony with more color added to the original chords. On top of this new harmony, we had a jam together with bass played by Thomas and drum by AI. In the final part of the piece, we went back to the original musical motif from Marcin and answered it musically with an open resolution to this dialogue between human and AI. Now Ray will provide some experience about our team's AI generation process and then show a short video of our final piece.
In this project, we first use AI to add both the harmonization and the drum to the music. First, we use the music transformer melody conditional model to harmonize the music idea proposed by the Marcin. Different from the transformer decoder model to continue the music generation, the accompany generation model is an encoder and a decoder transformer, which first encodes the melody input and uses the transformer decoder to output the accompaniment part. In our composition, the orchestra part is a result of AI. The Drumify plugin in the Ableton Live is used to add drum sequence. The visualization is realized by the HTML MIDI player JavaScript package. Now, please have a look at our composition and hope you enjoy it. Thanks for watching.
Thank you, Team 6. That video was amazing.
Thank you.
I'm so impressed with all you guys' work. And we actually, I think we have 3 minutes left. So maybe, does anyone want to say something about their whole experience during this hackathon? Because I can imagine it was quite tough working at a distance together with all these tools. Zane, how did you guys go about it?
For me, this hackathon was a really amazing experience because I can connect with people with different backgrounds. We have composers and programmers, and also people doing machine learning. And I think our team member has overcome the difficulty of the time difference and finally produced a very good result. And so we're very happy that we joined the hackathon.
Great. Anyone else? Did you guys have any life hacks to make this work? Amy, you're still awake, right? What time is it at your place?
I'm still awake. It's 6:30 now. I actually just didn't go to bed, but that's what a hackathon is about, right?
True. At least did you have some pizza and beer?
No pizza and beer.
Oh no. Well, I hope we can all even though this hackathon was amazing and the results are really very impressive, I really hope we can reconnect live maybe next year in Linz. That would be awesome.
I think we all want another week to projects now that we did a deep dive into them.
Yeah, but I mean, I hope that some of these projects will be developed further and maybe presented at the coming festival. But for now, I think the next program is up in the live stream. So I really want to thank everyone so much for their participation and all the effort and all the great work that you guys did. And I want to thank people out there for watching, and hopefully see you soon. So that's all from us, the AIxMusic Hackathon. Bye.